Hey everyone, welcome to The Explainer. Today we are unpacking what is absolutely, without a doubt, the greatest aerospace engineering triumph of the 21st century. For decades, the idea of launching a rocket into space and then flying it back down to a pinpoint landing seemed like total science fiction. I mean, the physics, the heat, the insane precision required, it's a seemingly impossible choreography. But today, orbital-class rockets are landing back on Earth like clockwork. We're going to break down exactly how they pull off this reusability revolution, looking right at the data, the hardware, and the incredible engineering that makes it all happen. Okay, let's dive into this. Here is our roadmap for today. We'll start with the macroeconomics in the reusability revolution, then look at classifying reusable rockets. After that, we'll zoom in on the mechanical precision with the anatomy of a landing and the enabling technologies. Finally, we'll zoom out to look at the upper stage challenge and the future of spaceflight. All right, Section 1, the reusability revolution, a paradigm shift in space economics. Look, for most of spaceflight history, we just sort of accepted this massive, glaring flaw in our economics. We were throwing away multi-million-dollar hardware after a single use. Traditional, expendable multi-stage rockets basically meant taking a beautifully complex $60+ million machine, using it for a few minutes, and just letting it fall into the ocean to be destroyed. It is literally like buying a commercial airliner, flying from New York to London exactly one time, and then tossing the plane in the trash. It's crazy. Reusable systems like the Falcon 9 flip this script entirely. By recovering and refurbishing that first stage booster, launch costs are slashed by an estimated 30 to 50% per flight. So why does this matter? Well, the absolutely crucial point here is that reusability fundamentally lowers the cost barriers to space access. And it's not just about saving money either. It's about sustainability. We are dramatically reducing the spent stages and debris that clutter our oceans and our orbits. This economic shift enables way more frequent science missions and actually makes space tourism a reality. Just to put that into perspective, listen to these ticket prices. While a fully orbital flight on a Crew Dragon still runs you around $50 million a seat, suborbital flights on reusable vehicles like Blue Origin's New Shepard have dropped to anywhere between $500,000 and $1.25 million. We are throwing the gates wide open. Moving right along to Section 2, classifying reusable rockets from small lift to super heavy. Now, not all rockets land the same way, right? And that mostly comes down to their mass. In the small lift class, vehicles like Rocket Lab's Electron use passive decelerators, like parachutes, followed by a splashdown in the ocean. They operate under incredibly strict mass constraints, which makes carrying heavy onboard fuel and landing legs totally impossible. But as we move up the scale to the medium, heavy, and super heavy classes, so your Falcon 9s, Falcon Heavies, and Starships, they all rely on propelled vertical landings. And notice something important here. While medium and heavy rockets currently recover just the first stage, the absolute holy grail in the super heavy class is full reusability of both stages. Okay, Section 3, Anatomy of a Landing, the Falcon 9 descent sequence. To really grasp this technology, we're going to do a gritty mechanical deep dive using the Falcon 9 as our primary case study. The sequence of events here has to be flawless. Here's the play-by-play. It kicks off at stage separation. The first stage drops away and cold gas thrusters at the top of the booster fire to flip the rocket 180 degrees so it's flying engine first. Second, the boost back burn. 3 of the 9 Merlin engines reignite to literally reverse the rocket's trajectory back toward the landing zone. Third is the entry burn. As it hits the atmosphere, the rocket is plummeting at around 3,000 miles per hour. 3 engines fire again, slamming on the brakes to slow it down to a much more manageable 560 miles per hour. And finally, the landing burn. Just moments before touchdown, a single center engine fires, slowing this massive vehicle to a gentle 5 miles per hour. Boom, touchdown. And this brilliantly illustrates the exact steps we just talked about. Depending on the mission profile and how much fuel is left over, this propelled vertical landing arc reveals a couple of options. It either takes the booster all the way back for a return to launch site, an RTLS landing, or if it's a high-energy mission, it follows a downrange ballistic arc to land on an autonomous drone ship waiting out in the ocean. Let's just pause and picture this for a second. We're talking about a 14-story building screaming through the upper atmosphere entirely backward at supersonic speeds, aiming for a target the size of a postage stamp in the middle of the ocean. The guidance, navigation, and control systems, the GNC, required to keep this structurally stable and perfectly on target, it absolutely defies human intuition. It's wild. Which brings us to Section 4, the enabling technologies. Grid fins, and landing legs. So how exactly do you steer a supersonic building? Well, if you've ever watched a rocket landing, you've seen the answer. Grid fins. They look kind of like heavy-duty waffle irons. They're actually a lattice-type control surface originally developed way back in the 1950s by Soviet engineer Sergei Beloskovsky for ballistic missiles. Unlike standard airplane wings, grid fins have a very short chord, meaning the distance from the front edge to the back edge is really small. And this is genius because it massively reduces the torque exerted on the steering mechanisms by high-speed airflow. You can use much smaller, lighter motors to pivot these fins. Now, what's really interesting about this slide is how fast this hardware had to evolve. Positioned in an X-wing formation near the top of the booster, these four fins independently adjust to control the rocket's pitch, yaw, and roll. But early on in the Falcon 9 testing program, SpaceX ran into a huge problem. The original aluminum grid fins were literally catching fire and melting due to the intense friction of atmospheric re-entry. No way around it, they had to upgrade. So they switched to cast and cut titanium. They're larger, they're heavier, but they can survive that extreme heat without even needing a blade of paint. And they allow the rocket to fly at higher angles of attack, a real game changer. Then, in the final nerve-wracking seconds, the landing legs deploy. And these aren't just simple struts. They're highly engineered components made of state-of-the-art carbon fiber, backed up with an aluminum honeycomb core to absorb the massive impact. Unfolding symmetrically in an instant using compressed helium, they stabilize the booster as it touches down on those autonomous ocean drone ships. You know, the ones bearing those fantastic names like "Just Read the Instructions." That leads us to Section 5, the Upper Stage Challenge, Surviving the Orbital Fire. Let's move to Terra and see how this builds upon what we've already learned. We've mastered the first stage, but to unlock the full potential of reusable spaceflight, we absolutely have to talk about the upper stage. Comparing these two trajectories side by side highlights the challenge perfectly. On the left, we have that first stage suborbital hop we just discussed. The first stage separates before the rocket gets going too incredibly fast. But on the right, the upper stage pushes the payload all the way into orbit. This means it doesn't just fall back down. It has to re-enter the atmosphere from a true orbital trajectory, which is a vastly more violent environment. Exactly how violent? Well, if an upper stage is returning from a high-energy trajectory, say coming back from a higher orbit or even another planet, it slams into the Earth's atmosphere at a blistering 11 kilometers per second. At 11 kilometers per second, the friction of the atmosphere generates thermal loads exceeding 5,000 watts per square centimeter. That is an absolute wall of orbital fire. Because of this, developing highly advanced, incredibly durable thermal protection systems, or TPS, is the single biggest engineering hurdle for upper stage recovery right now. These materials literally have to survive an inferno without significant degradation so they can be turned around and flown again quickly. Which brings us to our final topic, Section 6. The future of spaceflight, Starship and beyond. So if we can actually conquer these thermal and structural hurdles for full reusability, what does the future look like? When rockets get to the super heavy scale, everything scales up, including the dead weight of the landing legs required to hold them. So engineers started asking a radical question. How do you catch a super heavy rocket without legs at all? The answer, mid-air capture. Enter Mechazilla. The whole concept here is a tower-assisted mid-air catch, using these massive mechanical arms on the launch tower itself. By catching the booster right as it hovers, you completely eliminate the dead weight of landing legs from the rocket. This saves so much structural mass, which translates directly to carrying way more payload to orbit. This full reusability architecture is what actually makes wild ideas economically viable, like point-to-point Earth travel, where you could theoretically fly from New York to LA in 25 minutes, just by popping out of the atmosphere. But more importantly, this dramatic cost reduction is the foundational technology required to launch the sheer tonnage necessary for multiplanetary colonization. We're talking about building a base on Mars. Which leaves us with this final thought. We've gone from throwing away $60 million machines in the ocean to watching 14-story boosters land on targets at sea. As we master upper stage recovery and rockets truly begin to operate like commercial airplanes, are we finally on the verge of becoming a true spacefaring civilization? Well, looking at the data and these successful landings, the answer certainly seems to be yes. Thanks for hanging out with me for this explainer. Keep looking up, and I will see you in the next one.